Hello students, in this video we will study magnetic dipole moment of a revolving electron. We all know about the atomic structure. There is a nucleus at the center and electrons revolve around the nucleus. As in our solar system, the planets revolve around the sun. But the force of attraction here is due to the electrostatic forces in place of gravity. Also, the electron has two motions like the planets. One is rotational motion and the other is spinning action about its own axis and decides the properties of the material. Let us start. According to Bohr's model of an atom, the negatively charged electron is revolving round a positively charged nucleus in a circular orbit of radius r. The revolving electron in a closed path constitutes an electric current. The motion of the electron is anti-clockwise direction, which will produce the current in its opposite direction, that is clockwise direction. So it will behave like a current loop. And if it is a current loop, it will definitely have a magnetic dipole moment. See in this figure, suppose this is an electron which is revolving round the nucleus in a circular path and the radius of this circle is r. The mass of the electron is considered as m with subscript e. The velocity of the electron is v. As you can see that the electron is moving in anti-clockwise direction, so definitely the current will be in its opposite direction, that is the clockwise direction, like this. So we can say that as electron is revolving around the nucleus, it is moving in a circle, or you can say that the charge is moving in a circle. So it is equivalent to a current flowing in the loop, as we have just seen. So we can say that actually the revolving electron is like a loop of current. And if current is flowing, definitely magnetic field will also exist. And due to this magnetic field, a magnetic dipole moment will also exist. It tells us about the magnetic strength of the loop. Now, if you see carefully, this current is in clockwise direction. So, the upper phase will be acting as the south pole and the lower phase will be acting as the north pole. Hence, it acts as magnetic dipole. So, as it is a magnetic dipole, let us find its magnetic dipole moment. We know that current is equal to charge upon time. Here we have considered as electron, so we are considering the magnitude of the charge of electron, let it be E, upon time period t. And I have just told that r is the radius and v is the orbital speed of the electron. Now the time period can be written as distance travelled upon velocity. The distance travelled in circular motion by the electron is the circumference of the circle, which is equal to 2 pi r. So, by substituting the above time period expression in current equation, we will get as EV upon 2 pi r. Now, due to this circulating current, the magnetic moment is given by current into area, that is mu is equal to I into A. As it is a circular loop, so we can write area as pi r square like this. And now putting the value of the current I from the above expression, we can write the magnetic moment as EVR by 2. That is, we have simply kept the current I. See here, it is EV by 2 pi R into pi R square. So we will get EVR by 2. That is this expression. Now, in this expression, if I multiply and divide by the same quantity, that is the mass of the electron, it will not make any change in the given expression. But if you look carefully in the numerator, there is the term m into v. And what is mv? mv is the momentum. And if we are taking r also together, that is the electron is revolving in a circle, so it is angular momentum. That is mvr is angular momentum. So in place of mvr, angular momentum, I have written that notation capital L. As we know that electron is making circular motion around the nucleus, so it must be having some angular momentum. This angular momentum is only a mechanical quantity. But if you look carefully while rearranging the terms, this term E upon mass of the electron, that is charge upon mass of the electron, has some importance. This is specific charge of an electron. Specific charge of an electron. Now, if we put down the value of this specific charge of an electron in this expression, we will get this ratio, that is magnetic moment upon angular momentum. This ratio is a constant value and is called as gyromagnetic ratio, and its value comes out to be 8.8 into 10 raised to the power 10 coulomb per kg. We can find its unit from the above expression only, as in the numerator we are having charge. The unit of charge is coulomb and the SI unit of mass is kg. So we will get it as coulomb per kg. So we can say that the magnetic moment depends on angular momentum. As the angular momentum increases, definitely the velocity of the electron also increases. If velocity increases, its radius will also increase, and hence its area will also increase. What does it mean? If area is increasing, so its magnetic moment will also increase. Because we know the formula of the magnetic moment, which is equal to I into A. So if area is increasing, so magnetic moment will also increase. Now, according to Bohr's theory, an electron in an atom can revolve in certain stationary orbits, in which the angular momentum of electron is an integral multiple of h upon 2 pi. This is the Bohrs hypothesis, and he said that the electrons revolving around the nucleus can only revolve in certain stationary orbits, in which the associated angular momentum of the electron is an integral multiple of h upon 2 pi. So, let us put the angular momentum L equal to nh upon 2 pi, where n denotes the number of the orbit, that is first, second, third, or so on. And h is Planck's constant, and its value is 6.626 into 10 raised to the power minus 34 meter square kg per second. So we can put this angular momentum expression, that is nh upon 2 pi, which was the Bohr's hypothesis, in magnetic moment expression that we have obtained earlier. So we will get this expression, that is nhe upon 4 pi into mass of electron. So if you look carefully, all these terms are constant values. See, h is a Planck's constant, E is the electron charge, this is mass of the electron, and 4 pi itself is a constant. So you can say that the magnetic moment is equal to n times some value, that is all the terms are constant. So magnetic moment is multiple of n, which is the number of the orbit. Hence we can say that the magnetic moment is quantized and can have these values, where this is the least magnetic moment, that is when n is equal to 1, like this, that is the minimum value. So we have kept all the constant values in order to calculate the magnetic moment, and we have obtained it as 9.27 into 10 raised to the power minus 24 ampere meter square, which is called as Bohr Magneton. It is the minimum magnetic dipole moment because we have kept the value of n as 1, associated with an atom due to the orbital motion of the electron in the first stationary orbit of the atom. In addition to the magnetic moment due to its orbital motion, we know that the electron possesses the magnetic moment due to its spin also. That I have already told you. Hence, the resultant magnetic moment of an electron is the vector sum of orbital magnetic moment and spin magnetic moment, and hence determines the magnetic properties of the materials. That is the inherent property of the material. Thanks for watching. Please like, share and subscribe.